We live in a colorful world. Indeed, all around us, alike in our physical and inanimate environment and in the animate world of living things amidst which we dwell, nature has spread out a gorgeous canvas of color for our benefit. It would be superfluous for me to mention any examples of nature's artistry in color with which I am sure you are all familiar. We are ourselves but children of nature. It is no wonder, therefore, that we seek to imitate her and surround ourselves with a display of color. In the clothes that we wear, on the walls and floors of our houses, in all articles of household use, in the pictures which we hang up, and on the covers of the books which we read, we enjoy seeing color. Let us pause for a moment here and ask ourselves, is the show of color that nature puts out a needless display of exuberance, or has it a purpose or justification? It is sufficient if I refer here to the drama in color which is enacted every year before our eyes, when on the trees whose leaves have withered and fallen away in winter, the new buds come out and burst into life at springtime. As the season advances, the trees put on their canopy of green leaves to become a refreshing sight for our eyes. These green leaves of growing vegetation play a profoundly important role in the world of organic life, for they are the pathway by which life on our planet finds access to the energy of solar radiation. They furnish the means by which that energy is made use of for the sustenance of both plant and animal life. How this is done is a fascinating chapter of science which has some bearing on our present subject. Having placed pictures in color all around us, it would be unthinkable that nature had not at the same time provided us with the means for observing and appreciating their beauty. That indeed is the special topic which I intend to cover broadly in this talk. How do we perceive color? This is obviously a part of the larger question, how do we perceive light? And through light, the objects of the material world about us. These questions touch two great fields of exact knowledge, and a third field of which at present we have only some glimpses. The first field of knowledge is physics, and what it has to tell us about the nature of light, its properties and behavior. The second field is physiology, which concerns itself with the structure and functioning of the organs of sense, namely our eyes and their connections with the cerebral centers. The third field of knowledge lies where mind and matter meet, and we seek to penetrate the mystery of human consciousness and its awareness of the external world. It is by bringing the physical and physiological aspects of our problem simultaneously into focus that one can hope to find satisfactory answers on the material plane to the questions which interest us. That is the task which I set before myself some months ago, and the present talk is intended to place before you in simple and non-technical language the results of my labors during this period. I think it would be best if I begin with the physiological aspects of vision. The human eye has often been compared to a photographic camera. There are indeed some resemblances. In both cases, we have a small, light-tight box covered inside with dark pigment to absorb unwanted light, a shutter to exclude light when desired, and an adjustable diaphragm to regulate its admission when necessary. In both cases also, we have an optical system with the front and rear components capable of adjustment to form a focused image at the rear of the box. But to stress these structural similarities between a photographic camera and the human eye is rather misleading, since the basic purposes which they are respectively intended to fulfill are altogether different. A photographic camera serves to make a record of the light image on a sensitive film which can be developed and preserved. On the other hand, the retina at the back of our eyes is clearly intended to be both a receiver and a transmitter of energy. It receives the energy in the form of the light focused on it by the optical system in front, and it passes on the energy immediately to the cerebral centers, for if it did not, no sensation would be perceived. Whereas a photographic film can be used only once, the retina of the human eye is always ready for use. Indeed, vision would be useless to us if it did not carry with it the ability to view objects in different directions in quick succession, one after another. For the reasons stated, to compare the functioning of the human retina with that of a sensitive film in photography is neither useful nor enlightening. To understand more fully the mechanism of the perception of color, it is necessary for us to obtain inside knowledge of the nature of the living human retina and the manner of its functioning. When Helmholtz invented the ophthalmoscope and thus enabled our doctors to look inside our eyes and view their retinae, he made a gift of inestimable value to science and to humanity. With the many improvements since made, the instrument he gave the world is of the greatest value to practicing ophthalmologists. I have myself recently developed a new technique by which, without the aid of any instrument whatever, it is possible for a person to view his own retina in action and to observe how the different parts of it function in the perception of color. The technique is of extreme simplicity. The observer sits facing a white screen in a well-lighted room and views the screen through one or another of a suitably chosen set of color filters held close to the eyes. After allowing a sufficient time for the observer's vision to adapt itself to the effect of the color filter, the latter is suddenly removed. The observer then sees on the screen a highly enlarged image of his own retina, or rather of the physiologically important central part of it, known as the macula lutea. The nature of the image perceived and the color which it exhibits in different parts depend very much on the color filter used. With some filters, the effects are quite spectacular. The observer sees a highly magnified image of his own fovea as a colored disk of light with a bright spot at the center, which corresponds to the foveola or the central depression in the fovea. Surrounding the foveal disk appears a colored halo of considerable extension. The fovea, I should explain, is the most important part of the human retina. It is a disc about a millimeter in diameter, and when we direct our eyes to look at any particular object, its image falls on the fovea. It is the fovea that endows us with the acuity of vision needed to read fine print or to recognize a familiar face 100 yards away. To see your own fovea staring at you from a screen and exhibiting vivid colors is something of an experience. I cannot here stop to tell you in full detail all that the new technique has revealed. It is sufficient here to say that it has disclosed the existence in the human retina of three different pigments, which we shall call visual pigments, and which between them enable us to perceive the full spectrum of color, extending from the extreme violet to the extreme red. One pigment covers the violet and blue regions of the spectrum. The second pigment enables us to perceive the green and greenish yellow regions. The third pigment is principally effective at the red end of the spectrum, but it spills over into the orange and the yellow and overlaps in part the section in which the second pigment functions. It is necessary now to explain this statement that the visual pigments enable us to perceive color. The remark has already been made earlier in this talk that the retina is both a receiver and a transmitter of radiant energy. It is the pigment present in the retina that receives and absorbs the light energy falling on it. Immediately following such reception, the molecules of the pigment pass on the energy absorbed by them to the neurons or nerve endings present in the retina. Here the energy accepted is transformed into an electrical disturbance which is conducted through the optic nerves to the cerebrum. A pigment can obviously serve as a receiver only in the part of the spectrum which it is capable of absorbing. The efficiency or strength of such absorption is therefore also a measure of its ability to function as a mediator of vision. Modern physical theory tells us that light energy consists of discrete units or quanta, and that the absorption of light by the molecules of matter also involves discrete quanta. We are therefore justified in putting forward the view that the different parts of the spectrum appear to us as different in color by reason of the fact that the magnitude of the energy quanta varies from one end of the spectrum to the other, being least at the red end and greatest for the violet. As such variation is continuous, the number of colors in the spectrum distinguishable by the eye should be large. That is indeed the case. The number has been variously estimated as 150 to 250, the larger number being probably nearer the truth. Many investigators have studied the question of the limit or minimum of color difference which the eye can detect as we move from point to point along the spectrum. This limit or threshold varies in a remarkable way as we move through the spectrum, and these variations are highly significant in relation to the mechanism of the perception of light and color which I have indicated. The experimental findings demonstrate that the eye is highly sensitive to color differences and that it can detect a change in the magnitude of the light quanta received and absorbed by it of as little as 1%. In some parts of the spectrum, indeed, a change of as little as 1 part in 1,000 and the quantum of energy is perceived as a change of color. We are obliged by these facts to infer that the perception of light and color involves a simple transference of the energy absorbed by the visual pigment to the neurons in the retina. One of the 3 visual pigments has been identified with the plant pigment known as xanthophyll, present in all green leaves. It is capable of absorbing the violet and blue regions of the spectrum and hence enables us to perceive them. Its molecules are highly elongated and possess the special property that they can absorb light radiation only when its vibration is parallel to the length of the molecules. Within the fovea, the nerve endings are arranged in a radial fashion around its center, and the molecules of xanthophyll are therefore also disposed in the same fashion. It is possible to establish the features mentioned above and thus to demonstrate that xanthophyll is present in the retina and functions as a visual pigment by some simple observations. A brightly illuminated field is viewed through a color filter which transmits the violet and blue regions of the spectrum and cuts out all the rest. Simultaneously also, a Polaroid is held before the eye which limits the light vibration entering it to a particular direction. The observer then sees in his field of vision a picture of his own fovea in which a bright brush and a dark brush are seen crossing each other. When the Polaroid is alternately put in and taken out, the cross is seen to rotate backwards and forwards through the right angle. There are good reasons for identifying the other 2 visual pigments respectively with the ferrous and ferric forms of the blood pigment heme. The absorption spectra of these pigments appear respectively in the green and the red regions of the spectrum. They should therefore be capable of functioning as mediators of vision in those regions. Indeed, the greenish yellow section, where the absorption by the ferrous form of heme is most effective, is also by far the most luminous part of the spectrum.